So in this lesson, we're going to apply intermolecular forces to boiling points, and then I'm going to go into solubility. So I'm going to fly through the previous lesson slide to set your mindset and then give you something to practice. So intermolecular forces were the previous theme. We need to know the forces to predict boiling points. High forces, higher boiling point. Lower forces, lower boiling point. So we have three forces. Everything has London dispersion forces. The more electrons it has, the greater the London. Okay? Really, the bigger it is, the more London it has, but that's not the science, it's electrons. Then we talked about dipole-dipole forces. Okay? When you have a polar molecule that has a positive and negative end, you'll have these forces. You have to watch out for polar bonds that cancel each other out. They will not have dipole-dipole forces. Last, we had hydrogen bonding, which can be quite strong even in small molecules. So water-hydrogen bonds, it's really tough without a lot of London forces, but the hydrogen bonding dominates its physical properties. So now I'm going to give you some pairs to compare. I'd like you to figure out the forces between each of the molecules and then which one would have the greater boiling point. So your first one is CH4 versus C5H12. The second CH3OH versus C2H5OH. Okay. So you might need to take a few minutes, go back to first principles, and potentially draw these out. Okay. Others maybe can picture the molecules in their head. Last, I'm going to draw this one out. A carbon with 3 H's and a OH. Versus a single carbon with 2 O to H's coming off. So work on that for a bit. I'll recap the answers. I want a list of forces, and then you can just circle the one with the greater boiling point. If I asked you to compare melting points, it's the exact same thing. Whatever is the higher boiling point would have the higher melting point. So going through the forces and then what has the higher boiling point, the first question, I'll call that A, has C's and H's only in both of the examples. So hopefully when you notice that, you're going to put LDF on your list and you're not even going to think or look for dipoles. You're not going to look at electronegativity, you just stop there. The second one you may not fully picture, but it's C's and H's only. That will have 5 carbons in a row, and because the hydrogen count is double plus 2, there'll be all single bonds between all those carbons. Now that's a Chem 30 bit to realize that this follows the formula CnH2n plus 2. In Chem 30 we teach you this, and these have all single bonds between the carbons. You don't have to know that, but it's a shortcut to help you get the structure quickly. Okay? But again, that doesn't matter. So we're only comparing LDF forces, so the only thing we care about is electrons. The one with more electrons is the one with way more atoms. We're not going to count electrons. It's going to be C5H12. Okay? Methane at room temperature is a gas. It has boiled. Its boiling point is so low, it's already turned to gas. Okay? Where C5H10 is a liquid. I wouldn't expect you to memorize that, but it's an output of these forces. The forces in C5H10 is still holding them together in a liquid. Okay? And the name of the 5s, the 7s, we just use the prefixes that you kind of already know. What's a 5-sided shape? Pentagon. So we'll call that pentane next year in Chem 30. second example, you maybe needed to draw out. If you draw B out, you'll find that it is just the structure right below it. So CH3, carbon with 3 H's, then an O to an H. And I drew it bent. And it would help if you realize there's a lone pair that gives that bent shape. And so we have one of those O to H's, which is hydrogen bonding. So this is all the forces: London dispersion forces, dipole, dipole, and H bonding. In the other example, we have that OH again. We just have 2 carbons and then an OH. No, I didn't show all my hydrogen. I'm just going to put dashes. There should be an H at the end of each of those dashes. So that would be the look of our second option. London dispersion forces, dipole, dipole, and it also hydrogen bonds. So now when you're trying to figure out which one has the higher total forces, if we start with hydrogen bonding at the bottom, they both have 1 OH. So hydrogen bonding is actually a tie. Same OH, same electronegativity difference between hydrogen and oxygen, they each have 1. So that's a tie. So you'd have to look for another difference. And within Chem 20 and 30, we typically look at hydrogen bonding and London dispersion forces. Okay? So you have to go to London, and there's a distinct difference. There's a big difference in electrons in the second one. There's double the carbon count. Okay? Not quite double the hydrogen in 1O. So it's not double the electrons, but there is more electrons. So there'll be greater London forces in the second one. Okay? So that's going to break our tie, okay? And the larger hydrogen bonding molecule will have the higher boiling point. Bottom example, we've talked about hydrogen bonding in the one above it. We see OHs in both of these, so we have all the forces. And then we got to focus on the differences. I'll start at the top now. It really doesn't matter the sequence you go through them, but the top and the bottom are the ones we're going to focus on. So London dispersion forces, they both have 1 carbon. They both have 4 H's, but the one on the right has 2 O's. So that's going to give us more electrons. So there'll be greater London on the right. If we think of hydrogen bonding, the molecule on the left has 1 of those really extreme polar bonds, so we call hydrogen bonding, but the one on the right has 2 of them. And they never cancel each other out. You never get bond angles that they're pointing straight at each other. With the 109.5, they'll be pointing not symmetrically. So we have 2 times the hydrogen bonding on the right. So there's more London on the right, there's 2 times the hydrogen bonding on the right, so the right-hand one will have the higher boiling point. So that was figuring out boiling points. Okay. When can we mix an almost infinite amount of solute into a solvent? When do we have incredible high? Okay, we're not going to look at medium type solubility in Chem 20 and in Chem 30. So we have a couple circumstances that give really high solubility. The first is when we have nonpolar molecules in other nonpolar molecules. We'll have incredibly high solubility. So nonpolar molecules, these would only have London dispersion forces. And other nonpolar, so if they're nonpolar, they have to only have London forces. So LDF molecules and LDF only molecules will be highly soluble. So something that is purchased a lot, C7H16, you can buy that in a mixture of C8H18. You don't have to know this, but they're both liquids. You can mix them in almost any ratio. Okay. And thoughts of where would you go and buy this? There's stores that sell them quite regularly in fairly high volume. Okay. So Petro-Canada, Esso, this is sold by incredible volume. Okay. The world produces about 100 million barrels of oil per day, or that's what the world consumes. Okay. So this is our gasoline. So one example is LDF and LDF. They'll be highly soluble. The other possibility that gives high solubility is the other extreme, all the forces instead of the bare minimum. Molecules that hydrogen bond will be highly soluble in other molecules that hydrogen bond. Okay. This sets up a lot of the solubility for organic life. Okay. Organic life is water-based. And water has two OHs. Water can hydrogen bond. So molecules that can also hydrogen bond are going to be soluble in water or soluble in a living organism, us. So one of the simplest examples that I could pick that would have hydrogen bonding is methanol. They both have high forces. They're both liquids. So methanol in water would be highly soluble. I'm just writing the forces list. Sometimes I'll get students, they'll forget to put dipole forces, or if I ask them for the forces in water, they'll just say hydrogen bonding. Okay. They'll forget the others. Okay. You can mix any ratio of methanol and water. So you could go 5% methanol, 95% water, or 80% methanol, 20% water. You can put in more solute than you put in solvent, and it'll still mix because of the high solubility. So these are the two big applications of melting of intermolecular forces. Can you do boiling points? Can you do solubility? And you do all of this again in chemistry 30 when we do that carbon-based unit, organic chemistry. So I'd like you to determine whether the pairing I've put up is going to be highly soluble. You may need to do some drawing. Think of the forces. We've got carbon dioxide in water. We've got octane, where I've given you the formula of it in water. You've got ethanol in water, and you've got octane in hexane. So I'll give you some time as usual, and then put the answers up. Okay, so recapping the answers and going a little bit further using some pattern recognition. Our first one, carbon dioxide. So you've seen it in your notes a lot. Hopefully maybe you just remember that it's straight. There's two bonds and two lone pairs. Okay? The first bond away from each carbon is a sigma bond from hybrid orbitals. The double is from p's. Okay, but two bonds, no lone pairs, we get a linear molecule. So the polar bond on the right is equal to opposite to the polar bond on the left, and carbon dioxide only has London dispersion forces. And it's why carbon dioxide is not a liquid. Okay? If it had more forces, it might be a liquid, okay? But it doesn't, it's a gas at standard conditions. So LDF only in water, that is not going to be highly soluble. Octane in water. Well, hopefully you don't go too far with this. You see a hydrocarbon. This is London dispersion forces only. Water, you know, has all three. So that's not going to be highly soluble. Not soluble at all. That's kind of your oil and water. Okay, they don't mix. Okay, carbon dioxide isn't very soluble in water. Okay, the carbon dioxide wants to stay as a gas in the atmosphere, out of the water. Okay, small amounts, part per million amounts of CO2 does dissolve in water. Ethanol in water. So you see that OH, you either draw it out or you recognize that that's going to cause hydrogen bonding. So this has all the forces. I'm being a little lazy instead of writing all three out. Water, we know, has all the forces. So they both have hydrogen bonding. Last, we have octane, which I already up above put C8H18 in hexane, and these are, octane is C's and H's only, so that's LDF. Hexane is LDF, so that would be highly soluble in each other. You can mix them in any ratio, 70, 30, 80, 20, 90, 10, very soluble. Okay. So that's our solubility. And that wraps up the bonding unit. We did all the ionic stuff at the beginning, and a lot of your ionic knowledge just comes from Science 10. There wasn't a lot of new. Okay. The main difference was using lattice energies to separate melting points in something like aluminum nitride that has a +3 -3, which would have a higher melting point compared to a +1 -1 of the same size. Okay. What I haven't done, and will on this last slide is mix everything together. We're going to rank these three substances from high melting point to lowest, but we've got different types of chemical bonding here. So anytime you're asked to do either melting or boiling point, it's the same logic. If you're going to get the same list, we have to talk about forces. So first we have to realize what methane is. It's CH4. It was on a formula sheet in chem in Science 10. Hopefully it's a word you remember. It's such a common molecule. This is what's heating all our homes. So forces, that's C and H only, so it's LDF. So what holds one methane to another is London dispersion. Then we move over to sodium chloride. We have to do a big switch. Sodium chloride is a sodium plus ion and a Cl minus ion. If you weren't sure, you do electronegativity difference and find out it's greater than 1.7. So we're not going to list the intermolecular forces that we've been doing. We have to realize that this has ionic bonds. The sodium has a is +1, and it's got a Cl -1 holding it together. Incredibly powerful. Okay. Last, we have water, which this has all of our molecular, intermolecular forces. If we had multiple ionic compounds, we would use lattice energy to separate them out, their charges and their size. But we only have one ionic. Now, do ionic compounds are really high or low? You did a lab in Science 10 probably, where you might have put these molecules and ionic compounds in a hot plate to see when they'd melt. We've talked about it a bit. Ionic compounds are all super high, like 1,000 degrees in the difference. I think sodium chloride is 800 degrees just to melt, okay, where water melts at 0. So anything ionic will be by far the highest, and we're going highest to lowest, so that's going to be our number 1 by a country mile. Again, if you had 2 ionics, you'd look at charge and size to separate them. So that's our number 1, and then we can look at our molecules. So separate ionic from molecular. Now we've got to deal with the molecular. What is the next highest? Well, water's hydrogen bonding, and if you count the electrons, it's pretty much the same. Methane has 10, 6, and then 4 from the hydrogen. Water has 8 and 2. So you get 10 either way. So hydrogen bonding is the biggest difference. So water will have the second highest melting point, and then methane would be last with the least forces, so the lowest on the molecular list. So when you get an assessment question about melting points and you see something ionic, that's the highest by far.